Okay, so let's start. Hi everyone, again today. This session is about SeisSol, and I would like to introduce Vikas Koapati and David Schneller from Technical University of Munich. Both are PhD, right, or on plan to PhD, and then part of the developers of the applications. Vikas and David, just go ahead.
Yeah, let me quickly share my screen again. I hope I'm clearly audible to all of you. So welcome everyone. Today, my colleague and friend David and I will give you a very brief overview about what SeisSol is, what SeisSol could do, and the basic functionalities of SeisSol and the recent developments of SeisSol. If you have any questions, you could feel free to interrupt us at any point and ask your questions. So before I begin, I would like to give you a brief view of a couple of beautiful videos we have from the simulations which we made using SeisSol. On the left, the video which is running right now shows a showcase of the ridge crest earthquake scenario, and it is very interesting mainly because there were two events of earthquake which happened one after the other in this scenario, and we have branched faults with in this case, and it is a nice showcase for us to show that SeisSol could do something so complex. And on the right, we have another earthquake simulation from the fault in Iceland, and this was used to calculate some probabilities of hazard analysis in the Icelandic region. So these two are some nice showcases which we like to show every time, mainly because to show that we do something called as dynamic rupture to simulate the earthquake generations and then propagate the waves which are generated using SeisSol most of the times. And that being said, there are other functionalities of SeisSol which my colleague David would like to give a bit more detail.
Sure. Thank you, Vikas, for the introduction. So yes, as mentioned, SeisSol basically, and at least in the simulation scene, consists of mainly two parts. In this case, the first one is we have a rupture, a fault that's sort of like where friction is sort of like rupturing, and that's basically model. That's basically and that then emits waves into the 3D space around it. How that is actually modeled, what you've seen there is basically many small tetrahedra, and forming an unstructured tetrahedral mesh. And then the fault itself is modeled by phases. So basically on these tetrahedra. So it's basically modeled in 2D. The waves then propagate through these tetrahedra out into the domain. So in essence, it's 3D. Also, the question is, the method we're using to simulate the whole earthquake is called ADRDG. It's a discontinuous Galerkin method, which means that basically we mostly of the time only need to consider cells, only the small tetrahedra and their neighbors around them. And then during the wave propagates, basically one tetrahedron propagates information to the next, to its neighbors, and so on and so forth, starting at the fault. You have also the possibility to sort of like to just use zero-dimensional point sources, not maybe when you don't have enough rupture data, or if you have other data to use, then you can also use just point sources, which means basically just a point that suddenly emits something that then gets propagated in the domain. SeisSol itself also implements not only the elastic wave equation, which we are going to use here at ISC, but also viscoelastic materials, then elastic extension to viscoelasticity as well as poroelasticity, and also acoustic materials. So in principle, you can also simulate tsunamis on top of an earthquake simulation in one go. Then also in terms of output, you can also output anything that happens at some point in the domain. Sort of like try to reproduce any seismic writer, and also get an output, as you had seen before, of what happens on the fault and what happens in the domain. Again, these are all the tetrahedra itself, and we only provide one, in these simulations, one value per tetrahedron, and it just means that we have so many that it looks smooth. And yes, SeisSol can, as you have seen, deal with complex faults and complex model geometries and topographies. And also in terms of like how it is structured inside with the algorithm, is that the cells are clustered on their time step, which means basically that in the beginning, the cells, so elements that are maybe smaller or larger, then can be maybe or smaller, can maybe or have shorter angles, maybe can only be propagated at a smaller time speed. And so they get updated maybe twice as often or 4 times as often as larger cells, which are mostly or usually more outside of the domain, meaning that you only spend the computational power where it's really needed, but not too much anywhere else compared to when you have one time step in all places. So yeah, that was a very short overview over what SeisSol does. Anything to add?
No, yeah. That being said, thank you, David. So on a short summary of what recently have been developed using SeisSol, and so we have successfully ported our implementation to a lot of GPUs and supercomputers. Most of the top 500 machines have some kind of SeisSol optimization implemented at this point of time. So we have working SeisSol simulations on Frontier, Leonardo, Lumi, and Vista in the recent times. We have a particular project which uses SeisSol where we invert for multiple parameters using nonlinear rheology. In the recent Conway project, Conway is a Bavarian high-performance project. In the recent Conway project, we have implemented higher order output. And apart from that, we've really simulated a lot of real-world earthquake scenarios like the Sumatra, Tohoku, Japan, Palu in Indonesia, and the Turkey earthquake, which is really the task for this, and the Mendocino earthquake in the USA. And I hand over once again to David to give a brief overview on the higher order output.
Yes, so as mentioned before, if you have such a big mesh and so on, in principle, what you have is a polynomial on each cell. So from the mathematical or modeling perspective, you really have a polynomial, a 3D polynomial in each of the tetrahedra, and then which also gets propagated through the cell. Normally, however, and also the simulations you've seen in the beginning, and actually only use sort of like only output one value or maybe a bit subdivided value per cell. So what you can see on the left basically is when you take just a really, really, really coarse mesh here, exactly. Thanks for the pointing. And now now you just output a value, for example, at the very center of each cell. And as you can see, it does give some information, but it's not that much information as you would see on the right side, where it's really that sort of like we we output really a polynomial per cell, which is now a rather new development we had in the software. And just to sort of like show there is a lot more information hidden that maybe if you just output a barycenter or also with cell subdivision and then outputting barycenters does not even get shown that much. But it gets shown, it's still there, and it can still be outputted. And yeah, that's all about that.
So now I'm going to give you a brief overview of on a few of our real world simulated scenarios. But again, I'm going to give a brief overview. If someone is interested to know more about the earthquake physics or any more details on it, please contact us offline, because that way we could have a more or a deeper discussion. So that being said, the scenario which is being shown right now is the earthquake tsunami simulation, which occurred in 2004 on the Sumatra fault line. So the unique thing about this simulation was it was a big rupture which was extending over 1,500 kilometers, but the precision or the fineness of the mesh needed to be almost on a scale of meters. And it had a lot of complex geometry artifacts and a lot of shallow angles and everything. So this had almost 221 million elements, which translated to 111 billion degrees of freedom when we did it in a higher order simulation with ADG. And this was actually a good showcase for us to show how big of a simulation SeisSol can really handle and the capability of SeisSol. And this simulation was awarded the Best Paper Award in Supercomputing Conference in 2017. As a next step forward, this is another earthquake tsunami simulation which occurred in Palu in 2018. This was a step forward where on the left side we see a linked modeling, which means we simulate first the earthquake with the dynamic rupture, and then we take the ground deformations as the bathymetry inputs for the tsunami, and then run a shallow water equation to predict the tsunami's outputs. And as opposed to that, what was next developed was a fully coupled modeling, where we model the Earth as a solid and the acoustic layer of ocean together, and then run a coupled solver which solves them together instead of getting the earthquake data first and then running the shallow water equations. And this gave us a lot of challenges. This was solved, and this was then later done with the challenging geometry and meshing. And this resulted in another publication in Supercomputing Conference in 2021. And in this slide, we once again come back to the earlier Ridgecrest scenario. So the key point of this is this was more of a visualization challenge. This was done in cohesion with TAC, the Texas Advanced Computing Center, their visualization and data analytics. And this simulates two earthquakes on July 4th and 5th in 2029 with different magnitudes. It has multiple faults, which basically reveal that the earthquake can jump across segments when we have different branched faults. And there is actually a very nice video which was made by the TAC Visualization Center, but it's too long for this session, so we would not play it here. But if someone is interested, they could look it up. And this was another showcase where they used checkpointing. So in the end of the first simulation, you could basically save the simulation and then start a new simulation with the first simulation saved timestamp. This was an interesting development, and again, it came up with multiple challenges, but right now we have a working version of this. And yeah, so all these visualized scenarios have their data generated with SeisSol. And now to come to the main interesting earthquake scenario. This is the 2023 Turkey earthquake. If in the video you could see that there are two faults. So this created 2 different earthquake events in a short span of time in Turkey. And as a part of your first, or as a part of the virtual ISC task, we give you the first earthquake scenario. You run it, you visualize it, and of course not the way it is shown here, because this had a lot of filtering and a lot of different visualization tools used to create such a video. But in the end, if everything works out, this is something close to this is what you could generate. And as a part of the virtual task and at ISC, we give you a simulation data set, simulation parameter data set to generate the first earthquakes artifacts. And yeah, for the in-person task, we then gave the second earthquakes artifacts. As you could see that this is something really complex. So in theory, all you need is to just install SeisSol and run the simulation. But if there are any problems, please get to us. David will now give a very short, brief description of your task, and then we'll take it over from there.
Okay, yes, thank you, Vikas, again. So now, how does the task proceed? So first of all, of course, is to install SeisSol. There are instructions given both in the Atlassian wiki and also as a backup in our SeisSol Read the Docs documentation. And we recommend you to use version 1.3.1, which was released quite recently and contains unnecessary fixes, and so it has been confirmed to work on the British cluster. So use that version, and the installation can contain, as a warning, quite a bit of packages. So you'll have to install, for example, you'll have to install parameter in some graph partitioning method, and also code generators for matrix multiplications, because SeisSol basically just very roughly speaking consists just a lot of small matrix multiplications. And so you'll need a code generator for that. In our case, it's gonna be, I think, pspam we're gonna use, a channel generator from our group. There are also others like libxsmm, which can be a bit harder to compile, or which can also be used. And yeah, once you have installed all the components and built SeisSol itself, then once you have done that, then you can test the installation with some very small measures that we provide under the pre-computed SeisSol repository. For example, you can just take I think TPV5 or TPV33 should be good. Just to run it for a very short time, you will. It should be done really quickly, and then you can verify that your version of SeisSol you've compiled actually works. It outputs some values, it outputs some performance values, some energy values maybe. If they match roughly, you're good. So once everything is done, and I mean you've done the verification step, which we recommend you to do, but we do. Then it is to run SeisSol with the input files that are given on the wiki. That is, you have 4 CPU nodes, they have the 4 CPU nodes with the parameter files, and then just run this input. And also, we have given you a small or basis sort of script with some environment variables. It is important to use those because they set up the pinning of the cores. And SeisSol really depends on the correct pinning and correct setting up of the NUMA domains and everything like that to run efficiently. Furthermore, you'll have one environment variable you should play around with, which is this SeisSol conf thread. Well, it can be set to either 0 or 1. In the background, what it does, it basically reserves one whole thread for communication, which means to just like pull on MPI to get work done, to get the API implementation to do something, which, I mean, is interesting to see. Does it give performance right now? Does it not? It's in for a long time and we use it, but maybe something's changed, who knows? Also, for all of these values, SeisSol will output you 3 performance measures, which is for once the time to solution, which is important to note. Secondly, also one comparison measure, which we like to sort of use to compare also with past runs, which is the flops values. Sort of like we measure manually, count up the flops that we use in SeisSol, and there are like both the value of hardware and non-zero flops, which show you one of the hardware flops basically shows you how much work the CPU does, and non-zero flops shows you how much work actually gets done to the problem. So both of them are worth reporting. Then the next step is to profile the application with MPI and to answer the questions: which calls are used, the 3 most used MPI calls, and also maybe there's some improvement for them. Who knows? And finally, also with the results you're given, to create a short video with the results, you can visualize them in ParaView. And once you've done that, that's it. So yeah, I think then actually we're already
If
here
anyone
at the
has
end.
any questions, we are open for questions now.
And thank you for your attention.
Yeah.
Thank you, Vikas and David, and let's maybe open the stage for questions. Again, remember we're also on the Slack, so if you want to ask us later on as you go, just feel free. If anyone has any questions currently, I see one from on the chat.
Do you recommend using SPAC for building the dependencies, especially on an Arch 64-based system?
Well, yes, that works. Some of our colleagues already do that.
Yeah.
So you're free.
So feel free to try that.
Yeah.
For example, I have used SPAC on Frontera to build something like that. So, and we have, I think, already a SPAC repository with SeisSol on it. So
yes, actually, SeisSol is already upstreamed into SPAC itself. However, it may not, or at least it may be a tiny bit outdated at this point in time. I hope it changes in like next days or weeks.
Yes,
but
if something,
the dependencies should be up to date.
Yeah, you could try it, and if there's something which doesn't work or doesn't if you come up with a few problems, maybe we could look at it on the spot. Yeah. Are there any more questions?
Okay. Okay. If anyone has any questions, just speak. Anyway, if not, we will be on the Slack monitoring and try to. Oh, I see another question from Joseph.
Anything else to look out for regarding in-person competition? Is it pretty much the same except the data set? Yes, but for the second competition, you have a different data set which comes with an extra dependency. So as of now, you could make do without Asagi, which is a dependency. But for in-person competition, you would need Asagi because it has some netcdf files in it. There's another question: was SeisSol originally written in Fortran, or has it always been C++? So
that is a good. Yeah, sorry. Yeah.
Yeah, you could take this, David. It's fine.
Okay, sure. I mean, very good question. It was actually written in Fortran originally. So back in like I think 2012, it was a complete Fortran code, no C++ at all. And then gradually everything got ported over into C++ until like I think mid 2023 we got rid of anything Fortran related that was left, except a LabPack dependency for some equations. Yeah. But yeah, I mean version 1.1 still 1.0 still has Fortran as dependency.
Yeah, I mean lucky for me, that's exactly when I joined, and there's no more Fortran left. So. Any other questions? Yeah, I guess in that case, that's it, Ofer, or is there anything else?
Okay, so thanks everyone for joining. I would like to thank David and Vikas for the great presentation, and we'll keep the continued discussion on Slack. And again, if you have any issues, let us know. We'll have the interviews in mid-May, so I will schedule later on in April. 45 minutes per team, something like that, so you can describe your work on the applications and coding challenge. And I think that's it. So good luck, everyone, and we'll continue our discussions on Slack. Okay.
Yeah.
Okay. Bye, everyone.
Bye. Have fun, everyone. Good
Bye-bye.
luck.
Good luck.